In this section, I'd like to talk about pushdown automata. More specifically, we will cover three topics. First, we will compare finite automata, FA, and pushdown automata, PDA. Then we will go over the definition and details of pushdown automata. Finally, we will construct a PDA that recognizes a given language L. In regular languages, we talked about the equivalence of regular expressions and DFAs and NFAs. The equivalence between DFAs and NFAs means the non-determinism did not add any power to the finite automata. Now for context-free languages, context-free grammars are equivalent to non-deterministic pushdown automata, but they are not equivalent to deterministic pushdown automata. This means the non-determinism has added some power to pushdown automata. There are languages that can be recognized by non-deterministic pushdown automata, but cannot be recognized by deterministic pushdown automata. In previous sections, we have used the pumping lemma of regular languages to prove certain languages are not regular. Here are some examples. L1 is the set of strings containing consecutive zeros followed by consecutive ones, and the number of zeros is equal to the number of ones. L2 is similar. Now it has three parts: consecutive zeros followed by consecutive ones, and then followed by consecutive twos. Here it requires the number of zeros be equal to the number of twos, but it does not require the number of ones. L3 is the set of even-length palindrome, and L4 only cares about the number of zeros and the number of ones, but not care the order they appear in the string. For these four languages, they are not regular, proved by pumping lemma, and they are context-free. We can construct pushdown automata to recognize them. By doing so, we have proved these four languages are context-free. There are other non-regular languages, and they are also not context-free. For example, L5 contains the strings of zeros followed by ones followed by twos. And now it requires the number of zeros be equal to the number of ones and the number of twos. And this requirement for this number of ones makes this language non-context-free. And L6 is the set of strings that contains two identical parts. These languages are not context-free, and we can use pumping lemma to prove they are not context-free. This will be a topic for a later section. Now let's compare NFAs and MPDAs. For NFAs, we have states and transitions between states. We can transfer from one state to another when reading input symbols. The states are used to store some information. For example, if I reach a state A, the meaning of that can be the machine has consumed odd number of zeros. A DFA or NFA has finite memory because they have finite number of states. They only have those states to store the information. For non-deterministic pushdown automata, it also has states and transitions between states, but it also has a stack to store extra information. And it can transfer between states and modify stack when reading input symbols. Now both states and the stack are used to store information. An MPDA has infinite memory because the stack can store infinite many symbols. Of course, we still only have a finite number of states, so the information stored by the states is still limited, but we have an unlimited stack. Now let's go over the definition of a pushdown automata. A pushdown automaton is a 6-tuple. The first three parts are three sets: the set of states, the set of input symbols, and the set of stack symbols. This gamma and sigma can be different. Usually, gamma will contain some symbols that are not in this input alphabet. And all the three sets are finite. As for NFAs and DFAs, there is only a single start state for NPDAs. And F is a set of accept states, and F is a subset of this Q. Now let's analyze the transition function, which is the most important part of a machine. It maps a 3-tuple to a set of 2 tuples. For example, if I have QAB mapped to a set R1C1 or R2C2 and so on, the meaning of that is the machine is at current state Q and reading current symbol A from the input string, and the top symbol of the stack is B. Now following this transition, the machine will go to state R1 and replace the top symbol of the stack with C1. So it will replace the top symbol B with C1 if it chooses to go to R1, C1. Now let's analyze an example of an NPDA and go through the definition. The set of states are Q1, Q2, Q3, and Q4. And the input alphabet is 0 and 1. The stack alphabet is 0, 1, and the $sign. This epsilon is not a symbol in the input alphabet or the stack alphabet. It has a special meaning. It means nothing. You can treat it as an invisible symbol. For the first transition from Q1 to Q2, the meaning of that is if I'm at current state Q1 and I do not read any symbol from the input, and I replace nothing with the $sign. Replace nothing with the $sign means I will just add a $sign to the top of the stack. So this will set up the machine to contain a $sign at the very bottom of the stack. And this marks the bottom of the stack. For later computation, whenever you see this $sign, that means you have reached the bottom of the stack. And this last transition from Q3 to Q4. The meaning of that is, at current state Q3, consuming no symbols from the input string, and replace this $sign with nothing. Equivalently, we can say pop this $sign from the top of the stack. And the machine goes from Q3 to Q4. So this $sign is used to test for an empty stack. That means you have reached the bottom of the stack. You have popped out all the other symbols. And the first epsilon in the transition here also tests for the end of the input string. Now let's analyze another transition. This transition goes from Q2 to Q2, so the machine does not change states, but it changes the stack. So on current state Q2, the machine reads a symbol 0 from the input string, and then replace nothing with a 0, which means push a 0 down to the top of the stack. Let's go over the meaning of the transition again. If the transition is QAB to RC, the meaning of that is the machine reads a symbol A from the input string and replace the stack top symbol B with C and transfer from state Q to R. So in this case, epsilon is replaced with 0. That means I just add a 0 to the top of the stack. And this epsilon does not mean the stack is empty. It just means I will not replace any actual symbol from the top of the stack. I will replace an invisible epsilon symbol with another symbol 0. This transition from Q2 to Q3 can be written as Q2 1 0 to Q3 epsilon. The meaning of that is the machine transfers from Q2 to Q3 when reading an input symbol 1 and replace the top symbol 0 with epsilon, which means pop 0 from the stack. The final states of this machine is Q1 and Q4. The definition for a PDA to accept a string S is if it reaches an accept state after reading exactly all the symbols in S, just as the definition of the acceptance for an NFA or DFA. And for this definition, we don't care about the content of the stack. It can be empty, it can contain some symbols, doesn't matter. For this definition, we only care about that the machine land on an accept state after reading all the symbols in the input string. There is another definition of the acceptance of a string for this PDA. For that definition, the acceptance of a string S is if the machine reaches any state after reading all the symbols in the input string S, but with the stack being empty. For this definition, we don't care about what is the end state of the machine. We only care about that the stack is empty. Now let's analyze the meaning of these states and transitions. The top one will read zeros and store zeros in the stack. I want to remind you that these two zeros are different. The first zero is an input symbol from the input alphabet. The second zero is a stack symbol from the stack alphabet. It's not saying I'll read a zero from the input string and take that zero and put it in the stack. It's not that meaning. The meaning is I'm reading a zero from the input string. I'm not modifying the input string, and I cannot take that zero. I can just read that zero. The meaning of the second zero is I push a symbol 0, grabbing from the stack alphabet, and put that in the stack. Of course, you can use another symbol. When reading a 0 from the input string, you can push a star or a slash or a hyphen to the stack. That's also okay. That's legitimate. The meaning of this transition is when I read a 0 from the input string, I want to count this 0. I want to store the information that I have read a 0 in the stack. And I use a 0 to mark I have read 1 0 from the input. The transition circled by green means the machine will match all the zeros by ones. That means if you read a 0 from the input string, you will store a 0 as a counter in the stack. And when the machine starts reading ones from the input string, it will pop zeros out from the stack to match how many ones has the machine consumed from the input string. By doing so, if we have stored n zeros in the stack, then we can pop these zeros one by one once we read once. At the end, if there are equal number of ones and zeros in the input string, then after this Q3, the stack will be containing only the $sign. And at that time, the machine will not read any symbols from the input stream because it has reached the end, and it will see a $sign on top of the stack. It goes from Q3 to Q4 to accept this string. Since we are talking about non-deterministic PDAs, we don't need to specify every transition out of each state for each input symbol. All the missing transitions go to the trash state. Given the context-free language, how can we construct a PDA that recognizes it? For this language L, it has consecutive zeros followed by consecutive ones. But the number of zeros and the number of ones has a restriction. The number of zeros can be 0, but the number of ones need to be greater than the number of zeros. In the previous example, we asked for equal number of zeros and ones. Now we ask for more ones than zeros. If we are given this language, the first step we want to do is to analyze the property of the strings in this language. So since m is greater than or equal to 0 and n is strictly greater than 0, that means empty string is not in the language. And also, m is less than n, that means we have more ones than zeros in strings of this language. From these two observations, we know that the start state is not an accept state. And if we want to have more ones than zeros, we need to have a way to store all the zeros and then match all the zeros by ones. Finally, check if there are more ones left. Alright, to recognize this language, we first set up the machine by putting a $sign at the bottom of the stack, marking that that's the bottom of the stack. And that's the transition from Q1 to Q2. And Q1 is not an accept state because empty string is not in the language. Now we want to store all the zeros. And this transition does this function. When we read a 0 from the input string, we push a 0 to the stack and we store all the zeros. By doing so, we mark how many zeros we have read from the input string. Then we will match all the zeros by ones. Notice this transition from Q2 to Q3. It changed state from Q2 to Q3 while consuming no input symbols and do not modify the stack. And the transitions on Q3 are doing the job of matching all the zeros by ones. Every time the machine reads a 1 from the input string, it will pop a 0 from the stack. Now we have matched all the zeros by ones. We want to check if there are more ones than zeros. And it's done by the transition from Q3 to Q4 and the transitions on Q4. And the transition from Q3 to Q4 is to ensure there is at least one more ones than zeros. When we see a $sign on the top of the stack, that means we have popped all the zeros, which means we have matched all the zeros by ones. Now if we still see a 1 from the input string, we should accept this string. That means we have at least one more ones than zeros. And once we land on Q4, we can read more ones and still accept the string. Alright, that's the whole machine. You can do a proof to check this machine actually recognized the language L. But doing the proof is tedious. We can do a simple check by testing some sample strings. The principle to choose sample strings is to choose a string from each category. For this example, we have 4 categories. We have mixed zeros and ones. For example, 0101. This kind of strings should be rejected because it does not match the pattern of the strings in this language L. Another violation of the pattern is zeros after ones. For example, 10. For all the 3 other categories, they match the format of the strings in the language, but they have different properties of the number of ones and the number of zeros. The second category is the string has fewer zeros than ones. This kind of strings should be accepted. For example, 0111 should be accepted. The third one is the string has equal number of zeros and ones. Since m is strictly less than n, this kind of strings should be rejected. And for the same reason, if the string has more zeros than ones, the strings should be rejected. Let's check a string 0101 and analyze the computation. So at first, the machine starts at Q1 and it's not reading any input symbols. By following the transition from Q1 to Q2, the machine put a $sign to the bottom of the stack. And now the machine is at state Q2 and it's reading this symbol 0. By following the transition on Q2, the machine will land on Q2 and it will push a 0 to the stack. So after this transition, the machine is at Q2 and the stack has $0 sign in it. And the machine is about to read this symbol 1. If you check the transitions out of this Q2, there is no transitions for 1. Does that mean the computation dies? No, it does not, because there is a transition epsilon to epsilon. That means we don't need to consume any symbols from the input stream, but we can still do a transition. If that's the case, we don't have to read this 1. We can read nothing and do a transition. So following this transition from Q2 to Q3, the machine lands on Q3 and does nothing to the input stream and does nothing to the stack. But now it's at Q3. Now we check the transitions out of Q3. And we need to check the transitions start from a 1 because we are reading a symbol 1. There are 2 transitions for reading a 1 from the input stream. But we can only use the transition from Q3 to Q3 because the top symbol of the stack is a 0. So by doing so, the machine lands on Q3 and pop a 0 from the stack. Now we are still at Q3. We need to check transitions out of Q3 for symbol 0. And we found there is no such transitions, so the computation dies. This means we should reject this string. Similarly, for this string 1, 0, we start with the Q1 and an empty stack. Then we put a $sign to the stack and move to Q2. Now we are reading this symbol 1. Following the transition from Q2 to Q3, we change from Q2 to Q3 without consuming any symbols from the input stream and without modifying the stack. Now at Q3, we are reading a 1 and we see a $sign on the top of the stack. So we should transfer from Q3 to Q4. The machine does so by landing on Q4 and pop the $sign from the stack. Now the machine is on Q4 and it should read a symbol 0. But we check the transitions out of this Q4 and there's no transitions for 0. So the computation dies and we should reject this string. Another example, this string only has a single 1. Starting from Q1, without consuming any symbols from the input stream, the machine lands on Q2 and put a $sign to the top of the stack. Now at Q2, we need to read a 1, but there is no transitions for 1. But luckily, there is a transition for epsilon, so we can follow that epsilon transition from Q2 to Q3, which means we do not consume any input symbols and we do not modify the stack. Now at Q3, we are reading this input symbol 1 and we see a $sign on top of the stack. That means we should go from Q3 to Q4. After that, we have consumed all the symbols from the input string and we have reached an accept state. That means we should accept this string. I'll leave all the other examples for you as a practice. Leave a comment if you have any questions.